So what separates part 2 from part 1? So just as a recap, since it's been a while, what did we do in the last class? We practiced converting weight in milligrams, how much it weighs, to how many molecules are in that weight. So how do you convert from weight to molecules? What do you do with the weight? You divide by the formula weight or the molecular weight. Very good. So we convert a weight to the number of moles or millimoles by dividing by the molecular weight. How do we go from millimoles then to milliequivalents? We don't divide, we multiply by the valence. So do you remember then, we had a lot of questions where we took a weight, we converted it to millimoles, and converted millimoles to millimoles of a particular ion, because remember, these drugs that we're talking about are all dissociate. So in solutions, they dissociate to anions and cations, and then we can measure the electricity in terms of milliequivalents. So today we're doing the same thing and including that, but instead of going to milliequivalents, sometimes what we want to know is how many particles. Why is that important? Tonicity. Remember chapter 11, we talked about trying to make things isotonic or tonicity. So we have to know essentially the tonicity of the solutions, and we measure that in milliosmoles. So we're talking about the osmolarity of the solution. Osmolarity, milliosmoles per liter is osmolarity. So we'll be talking about the osmotic forces that are driven by that. And in that case, it's not by the charge, it's by the number of particles. So today, be ready to count particles, which makes you apply a little bit of your chemistry because you have to look at the formula and to be able to determine that, okay? So let's work through number 1 together, and because it's kind of a silly question, but it makes you practice this idea of going to milliosmoles, because it says to calculate the millimoles, the number of molecules, and the milliosmoles, meaning the number of particles, for starting with 1 gram of each of these. So go ahead and do this. Go ahead and convert millimoles or convert to millimoles. So if I start with 1 gram of mannitol, 1 gram, be careful, 1 gram of mannitol, convert that to the number of millimoles. Then we'll go to milliosmoles here in a second. The trick to that was, did you know 1 gram, we need to get into milli. Since we want milliosmoles, we have to get and start with milligrams. So 1 gram is 1,000 milligrams. And then we just take the molecular weight and divide by that in milligrams. And did you all get 5.5 millimoles? Easy enough, okay? Now here's the deal. You go from moles, we don't worry about milliequivalents. When we're doing milliosmoles, we go from the number of molecules to the number of particles. And so what is the difference in your mind? Can you picture a molecule? Like sodium chloride. Let's take that as a good example. In your molecule, sodium chloride, how many parts are there in it? 2, right? There's sodium and then chloride, and they're stuck together, right? Because of the valence, because of the charges. A plus with a minus, they stick together. But you put them into solution, they dissociate. So 1 molecule has how many particles? 2 in the example of sodium chloride. Now, do all drugs dissociate like our electrolytes do? No, and mannitol is an example, and I will always tell you this on a test, but mannitol is an example of a drug that does not dissociate, okay? You stick a mannitol in the water, and it just stays as mannitol. So if I stick 1 particle or 1 molecule of mannitol, how many particles do I get? 1. It's 1 to 1. Some things do not dissociate. Since mannitol does not dissociate, this is where I'm saying it's a non-electrolyte. It doesn't dissociate. So you get 1 milliosmole from every 1 molecule, basically, because it doesn't dissociate. It stays whole. So obviously you get 5.5 milliosmoles because you got 5.5 millimoles. Since 1 particle for every 1 molecule, you get the same number. All right? So I'll let you do both steps for this one. So now calculate the number of millimoles and the number of milliosmoles for, in this case, ferrous sulfate heptahydrate. All right, I give you the formula. You're going to need to know the formula and the molecular weight there. I hope that you get this kind of light bulb moment because both milliequivalents and milliosmoles are pretty simple. As soon as you can visualize particles, electricity, molecules and the relationship between all of them, these calculations become pretty straightforward. So again, 1 gram is 1,000 milligrams. We divide that by the molecular weight in milligrams, and we come up with 3.6 millimoles. So we'll start with 3.6 millimoles. Everyone okay with that? Now here's the deal. You have to look at the formula and decide. When ferrous sulfate heptahydrate dissociates, what will it produce? It will produce 1 iron, 1 sulfate. Can you separate your cations from your anions when you look at this? I'm not teaching you that. This is the chemistry you have to kind of bring with you a little bit here. So you have iron plus 2 and 1 sulfate minus 2. So that's where that formula makes up. So we have one of those. What about these? This is always what throws students off. What about the heptahydrate? Are those particles? No, that's the solution the particles are floating in. So we do not count water molecules as particles. And that is a trick that just to learn that. Remember, when we're talking about dissociating, we are talking about dissociating in water. So the fact that 7 water molecules came along in the end doesn't matter. It just becomes part of the water. In the end, we only have particles of iron and sulfate. Those are the only particles that are going to produce osmotic forces in the water. All right, so in this case, we have 2 particles generated for every 1 molecule, if you will. So 2 milliosmoles for every 1 millimole. So we multiplied 3.6 times 2, and you got 7.2. All right, do the same thing. And go ahead and do the rest of these questions. I think, how many are there? 5? Yep, go ahead and do sections 3, 4, and 5, or parts 3, 4, and 5. They all work the same. The molecules are different, so think about how many particles each of those molecules will release, if you will. So the big thing here is we start with 1,000 milligrams, we divide by the molecular weight so that we end up with 5.7 millimoles of, of dibasic potassium phosphate. So we start with that. The question is, what does this turn into? Well, it turns into 2 potassiums, okay, and 1 dibasic phosphate, okay? So that gives us 2 potassiums and 1 phosphate. That's how many? 2 plus 1 is 3. Would you agree? So that's where the 3 comes from. So is everyone okay where the number that comes in the front? It's from the total number of particles. 2 potassiums from the formula K2 and 1 dibasic phosphate from the HPO4 gives us a total of 3 molecules. So we multiply the millimoles by 3 and I got 17.1. Okay. How did we do on aluminum hydroxide? Again, 1,000 divided by 78 gave me 12.8. So starting with 12.8 millimoles, then looking at the formula, we get 1 aluminum, but we get 3 hydroxides. So 1 aluminum plus 3 hydroxides is 4. That's where this number 4 comes from. 4 times 12.8 gave us the 51.2. Okay, are we getting a little pattern down here? I know this is not mind-rending, but you got to look at the formula. So again, for trimagnesium dicitrate, we again convert by dividing by the formula weight. We get 2.2 millimoles, but then looking at this formula down here, there are 3 magnesiums and 2 citrates. So 3 plus 2 is 5, so the total of 5 particles generated from every 1 molecule. 5 times 2.2 gave me 11. How did we do? Okay, so let's do a real question now. Those were kind of introductory things. So now that you kind of know how to do all this, let's apply these to different questions here. And again, these questions are all step by step broken down a little bit, certainly more than you would expect to see on the exam or on the homework. So step 1 though, says a 10 mil vial of 0.03% manganese sulfate with the MnSO4.H2O, so manganese sulfate monohydrate, solution is used for providing trace elements for a total parenteral nutrition. The TPN we'll be talking about on the next one. So we have this size vial of this concentration of that electrolyte. All right, so the first question, go ahead and it says, how many millimoles of manganese sulfate monohydrate are in the 10 ml vial? So step 1, tell me how many millimoles in the entire vial. So we started with 10 milliliters, and that's a volume, and we're going to use our concentration of 0.03% weight per volume, meaning 0.03 grams per 100 milliliters. We multiply that times the 10 milliliters, we convert milliliters to grams. And remember, since we're always going to want millimoles and milliosmoles and milliequivalents, we're going to do everything in milli. So we're going to multiply by 1,000 to convert grams to milligrams. And lo and behold, at that step, I have simply converted my volume to my total weight of 3 milligrams of manganese sulfate, monohydrate. So I start there. Now to convert that to millimoles, I take the formula weight, and divide by that so that the weight of milligrams gets converted to millimoles, and I get 0.02 millimoles of manganese sulfate. At this point, we let go of the water. The water is in the solution. Once we put it into solution, it disappears. What we have left is the actual number of molecules of our manganese sulfate. Now, this is going back to the part 1, so we're not going to forget milliequivalent. So simply, now that we know, and again, you're going to want to keep using this value here a lot, because that's our source. What we have is 0.02 millimoles of manganese sulfate. From that, how many milliequivalents of manganese do we have? So start from our previous answer and do really one step to convert millimoles into milliequivalents, okay? When I say one step, it's really 2 steps, but convert 0.02 millimoles of manganese sulfate into milliequivalents of just manganese. All right, the trick there was, so this is what we had on the previous screen. All right, so what is the relationship, though, we need of manganese, right? We don't want manganese sulfate. So what's the relationship between manganese sulfate and manganese? It's 1 to 1. There is 1 manganese, right, in every 1 molecule of manganese sulfate, so 1 to 1. So that converts millimoles of manganese sulfate to just millimoles of manganese. And then what do we do to convert from molecules to milliequivalents? Is the valence. So it's the charge on manganese is a +2. That means you get 2 what? 2 milliequivalents, that's the unit for charge, 2 milliequivalents for every 1 millimole of manganese. And so 2 times 0.02 gives us 0.04 milliequivalents of manganese. Okay? That's what we did before. Let's do something a little bit different now. Let's introduce the idea of osmolarity. Osmolarity is the number of particles, just like we calculated milliosmoles, but to standardize it, we make it into a concentration. In terms of, we say milliosmoles per liter. So whenever you see osmolarity, especially the larity, that means the number of milliosmoles per liter, right? So we got to keep that in mind. So I want to know what is the I want to know the osmolarity. So I'll need to know, obviously, the total number of milliosmoles divided by the volume, essentially converted into liters. I want to express it per liter, all right? What's the first step? The first step would be to convert 0.02 millimoles. Remember, we know the number of millimoles. We had 0.02 millimoles. So how many milliosmoles is that, okay? So again, what I've done is I've put, there's my millimoles, and remember it's a 10 ml vial. So I have that number of molecules, 0.02 millimoles of molecules in 10 milliliters. Now let's not worry about the 10 milliliters yet. Let's set up this first. So really, we're already in millimoles. All I have to do is look at the formula for manganese sulfate and see that I get 1 manganese and 1 sulfate. So the total is 2. So essentially 2 milliosmoles for every 1 millimole. So if I multiply like that, millimoles will cancel, and I'll be in milliosmoles, but I'm still per milliliter. What do I want to be in? Per liter. So I just need to express or convert 10 milliliters to liters. So that's where I multiply by 1,000 mils per 1 liter, and that gives me this unit along with this unit. So 0.02 times 2 divided by 10 times 1,000 gives me 4 milliosmoles per liter. So first of all, could everyone set this up? Do you see where that came from? That came from our calculated amount of milliosmoles that were in the total vial, and the total vial volume is 10 milliliters. So once you set this up, it really was just a matter of unit conversion from millimoles to milliosmoles and milliliters to liters. All right? Now, let's practice that some more here. This is a great question. I like this question. It puts lots of things together in this. And in this case, we've got 3 ingredients. We have an IV bag, an intravenous bag that contains potassium chloride at a concentration of 0.15% weight per volume, in a solution containing both 5% dextrose and 0.45% sodium chloride. So there are 3 ingredients in here. Okay, so we're going to have to do 3 things for each of these calculations. The first thing, and really you'll see that to calculate milliequivalents or to calculate millimoles, we need, or milliosmoles, we need the number of molecules. So you almost always go from a weight to the milliosmoles first as your first step. So that's what I'm telling you to do here. First thing we need to do is convert our number of our weight in grams to milligrams, and then milligrams to millimoles. And I'll just show you my work for the sake of time. It's doing the same thing 3 times. So these are 3 different formulas, one for potassium chloride, one for dextrose, and there's my sodium chloride. So So let's just analyze one in detail. We are starting with a 1 liter bag. So could you start with 1,000 milliliters? We're starting with 1,000 milliliters. And for the potassium chloride, what is our concentration? 0.15% weight per volume. So that means 0.15 grams per 100 milliliters. That's why we started with milliliters, because if I multiply by that, I can convert my 1 liter bag, my 1,000 milliliters, to a grams of sodium chloride. Everyone okay with that? That's chapter 6. We practice that. That's where we can convert a volume to a weight using a concentration of weight per volume. Then I got to convert grams here to milligrams. So let's go ahead and multiply by 1,000. So simply that weight, instead of being in grams, is in milligrams. That's all I've done, is taken my volume times my concentration times 1,000 to get into milligrams. And then lastly, to get to millimoles for potassium chloride, all I have to do is divide by the formula weight in milligrams, and voila, I have 20 millimoles. So, looking at each other formula, can you see how I did that? So, the dextrose was 5%, so that's where I changed that step. Its molecular weight was 198, so that's where that came from. Doing the same thing from sodium chloride, there's its percent, so that's why that number comes from. And its molecular weight is 58.14. So do you see where I'm just changing 2 numbers in each one of these setups, but the setups are exactly the same. You take the volume times the concentration to get it in grams, times 1,000 to get into milligrams, divide by the molecular weight to get into millimoles. Got to get into that routine and be able to see that structure and how you go from one to the other. Okay, so again, now that I've got millimoles, I know how many molecules for each of those. So what does the next question want? Well, for the electrolytes, and the only 2 electrolytes, dextrose is not an electrolyte. That means there's only potassium chloride, which will split into potassium and chloride, and sodium chloride that splits into sodium and chloride. So of those 2, calculate the milliequivalents. How many milliequivalents of potassium and sodium are in this bag? Where would you start with? Well, we could start with at the very beginning again, but we already know how many millimoles. Remember, we've got 20 millimoles of potassium chloride and 253 millimoles of not dextrose, 77 sodium chloride, 20 of potassium chloride. So let's start with that. So we're not redoing that work. Understand these numbers come from the work we have just done. That's simplifying our steps here. So we have just calculated for potassium chloride that we have 20 millimoles. All right, so I want to know of milliequivalents of potassium. So I've got to go from potassium chloride to just potassium. The formula is 1 potassium for every 1 chloride, so it's 1 to 1. So that converts essentially potassium chloride to potassium. And then the valence, or the charge on potassium, is 1. So there's 1 MEQ for every 1 millimole. That means I get an equal number of milliequivalents. And guess what? Sodium chloride is exactly the same. There's 1 sodium in a molecule of sodium chloride, and there's a 1 charge on a sodium. So you'll notice you have the same number of milliequivalents of sodium as you did millimoles. Now let's get to milliosmoles. All right? So milliosmoles are not valence, it's particles. But do you see where we're starting with the number of molecules? And these are everything we did in the first part. So we start with the number of molecules. In this case, we had 20 millimoles of potassium chloride. Now when they dissociate, I don't care about the charge or the electricity, I care about how many things come out of that. So in this case, out of potassium chloride, I get 1 potassium and 1 chloride, so I get 2 things. So if I start with 20 of the molecules, times 2 gives me 40 particles. 20 molecules become 40 particles. All right? Dextrose, start with 253, it's non-electrolyte. It doesn't dissociate, meaning every molecule has just 1 milliosmole, so I get an equal number of 253 milliosmoles from the dextrose. Sodium chloride, again, sodium and chloride split, so you get 1 sodium and 1 chloride. Those are 2 things here. So 2 times 77 gave me the 154 milliosmoles total. What was the osmolarity? All right, so we have individual osmoles, and they're just additive. It doesn't matter in a solution whether the milliosmoles comes from a sodium or potassium or dextrose. It's all the force generated by that number of particles, regardless of what the particles are. So to calculate osmolarity, we just add up all of the individual milliosmoles and get a total. There's our total, and remember, this was an easy one because we're starting with a 1 liter bag, so we're starting per 1 liter, so we have 447 milliosmoles per liter as our final amount. All right, I think we've worked through all the permutations here a little bit. If you can do all of those things, you can do these questions. So again, in this situation, we're talking about magnesium sulfate, which is weird. Did you realize that you can actually, it's a muscle relaxer. So sometimes when somebody goes to the emergency room and they're having a really bad asthma attack, you think you give them some albuterol, which is a beta-2 agonist, which tries to stimulate it. But if that doesn't work, then they can give this electrolyte, magnesium sulfate, and it actually directly relaxes the muscle. So in that case, what we want to do is give somebody a 2-gram dose. So in the end, how many millimoles of magnesium sulfate are administered when we give 2 grams of it? So we'll start with a 2-gram dose, okay? And we want to be in millimoles, so let's get everything into milli. So I started by, and you don't have to do it in this order, but I converted my grams to milligrams by multiplying by 1,000. And then remember then to convert from the weight of something to the number of molecules, we divide by the molecular weight. So the molecular weight is here. If I express that in milligrams and divide by it, that will convert my milligrams to millimoles. And I got 8.1 millimoles of magnesium sulfate. Okay? Now, 2 separate questions. Part 2 and Part 3 aren't related to each other, but they all start with the 8.1 millimoles. So from that number of molecules, how many milli equivalents of magnesium do you get? Well, that's what we're starting with. We just solved for 8.1. So how many magnesiums in a magnesium sulfate? It's 1 to 1. So there's the one that converts from millimoles of magnesium sulfate to millimoles of just magnesium. But to go from millimoles to the number of electricity, remember the E in milli equivalence stands for electricity, and that comes from the valence, all right? So the charge of magnesium is 2, so there are 2 milli equivalents for every 1 millimole. So that's where you get 16.2 milli equivalents of magnesium from the 8.1 millimoles of magnesium sulfate. Okay? Now, let's do something different. Instead of milli equivalents, I want milliosmoles. Instead of counting electricity or charges, I'm going to count what? Particles, the number of particles that come from when my chemical, magnesium sulfate, dissociates. So if I start with 8.1 millimoles of magnesium sulfate and look at the molecule here, I'm going to get 1 magnesium and 1 sulfate. So 1 plus 1 is 2. 2 particles from every 1 molecule, if you will. So if I multiply my 8.1 molecules by 2, I see that I get that same number, but in this case, I'm counting particles. So it's 16.2 milliosmoles, the number of particles from my magnesium sulfate. Okay? So we know we have milliosmoles, but now we got to think a little bit about volume here because I'm working up to osmolarity. And remember, osmolarity was milliosmoles per liter. So in the end, volume is going to become important. And I know that I have this many milliosmoles, but we haven't dealt with the volume of anything yet. So let's deal with that. So first of all, the volume, I need to calculate how much magnesium sulfate I need. It comes in a 500 milligram per mil solution. And remember, I wanted 2 grams. So this is going back to essentially maybe chapter 7, 8 kind of thing. How many milliliters of this will provide me this? So don't make it difficult, but again, we have grams and we have milligrams. So the first thing to do is convert 2 grams to milligrams by multiplying by 1,000. Then let's use my concentration and divide by 500 so I can convert from milligrams to milliliters. And hopefully you can easily see where 4 milliliters of a 500 milligram per milliliter solution, because 4 times 500 would be 2,000. 2,000 is equal to 2 grams. So that's how much I need of just giving the magnesium sulfate. And guess what? Some drugs you can directly inject straight into the blood, and we would just inject 4 milliliters. But this is not one of those. That would be dangerous with this drug, so we have to dilute it. Okay, and this is something you just look up in a thing like maybe like Lexi drugs and would look up how do you administer magnesium sulfate, and it says it must be diluted with at least 100 milliliters and it's compatible with 5% dextrose. Oh, so not only will I have magnesium sulfate, my drug, but I'm going to also have to administer it in dextrose. Why can't I just inject it in water? Water would not be isotonic with the blood that I'm going to be injecting it into. So I've got to put my drug in an isotonic solution, but that isotonic means there's a certain amount of milliosmoles already in that solution. So even though I know my millimoles of my drug, I now need to know milliosmoles. I need to find milliosmoles of my solution. So, and again, to make this difficult, it's 100 milliliters of that solution. It is a 5% dextrose solution. So 100 milliliters times 5 grams per 100 milliliters means there's 5 grams of dextrose. 5 grams of dextrose is equivalent to 5,000 milligrams of dextrose. That's not just changing units there. Now that I've got 5,000 milligrams of dextrose, I need to convert it to the number of molecules of dextrose. So I'm going to divide by the molecular weight. And when I do that, I convert from the weight to the number of molecules. So now I know how many molecules of dextrose. And lastly, to determine the milliosmoles, I'm going to count particles. And since it's a non-electrolyte, I shouldn't have crossed it off, I'm supposed to underline, there's 1 milliosmole for every 1 millimole because it does not dissociate. It's 1 to 1. So you do that math all the way across and you see that you get 25.3 milliosmoles of force just from the dextrose solution. So in the end, what we're going to need to do to calculate osmolarity is we have to take the milliosmoles from my drug plus the milliosmoles from my dextrose solution, add that all together. So the combined total is 41.5 milliosmoles. That goes in the numerator of my total osmolarity. Okay? That's the easy part. The other thing to remember here, not to be confused of, is we used how much dextrose? It was a 100 milliliter bag of dextrose, right? But what did we calculate for the magnesium sulfate? 4 milliliters. So remember, the total volume of it combined is 104 milliliters, not just 100. Okay? Now we need a liter, so let's just convert 104 milliliters to liters by dividing that by 1,000. So really the 104 milliliters is 0.104 liters. That's my total volume. So my total milliosmoles divided by my total volume, divide that out, and I got 399 milliosmoles per liter. All right? All right, this one is a deceptively difficult question. It seems easier, but it's a little bit more difficult. So I'll just walk you through this one. It says a physician wants exactly 500 milliliters, so there's my volume, of a 3% concentration of sodium. Where does that sodium come from? Are there different sources of sodium? Absolutely. So I can make a 3% concentration of sodium using different things. What I want to use is exactly a third of the sodium needs to come from sodium chloride, whereas the remaining 2/3 need to come from sodium acetate. So we have to do the same sort of calculations, but once with sodium chloride, and then again with sodium acetate, and make sure that we have enough that 1/3 of the sodium comes from sodium chloride, and 2/3 of the sodium comes from the sodium sulfate, or sodium acetate. All right? So in the end, though, where do we start? We need to know how much sodium we need. Who cares where it comes from yet? I need to know how much sodium. The first question is, regardless of my source of sodium, how much sodium do I need? Well, I want 500 milliliters of a solution to be 3% weight per volume. So 500 mils times 3 grams over 100 mils tells me I need 15 grams of sodium. Now I can start to partition that sodium between the two different ingredients. So starting with the first ingredient, if we start with sodium chloride, so how much should come from sodium chloride? Well, if my total is 15 grams and I want 1/3 of that to come from sodium chloride, 15 divided by 3 means I need 5 grams of sodium from the sodium chloride. Is everyone okay where the 15 came from? That's the total of everything. If 1/3 of it comes from sodium chloride, 1/3 of 15 is 5. So I obviously need 5 from sodium chloride. I'll need 10 from the sodium acetate, but let's worry about the sodium acetate later. Let's focus on the sodium chloride. Because I now know that I need 5 grams of sodium. Well, how many grams of sodium chloride are required to provide the required weight of sodium? Remember, our 5 grams was of what? Sodium alone. So that's what we need to start with. I have 5 grams of sodium. So how much sodium chloride would that be? Well, I need to convert from grams of sodium to the number of molecules. 5 grams of sodium divided by 23 gives me the moles of sodium. All right? Now I can convert from the number of moles or molecules of sodium to that of sodium chloride by what's the relationship? There's 1 sodium in sodium chloride, so it's 1 to 1. So now I can convert sodium to sodium chloride, And then lastly, I can convert from the number of moles of sodium chloride to the number of grams by multiplying by the formula weight. Because again, for every 1 mole, there's 58.4 grams of sodium chloride. So going across like that, do you see where I was able to convert that essentially 5 grams of sodium is contained in 12.7 grams of sodium chloride. All right? Now I have a target. That's the target of sodium chloride that provides what I want, which is 5 grams of sodium. So let's go forward with this and figure out how are we going to get that. We are going to use a 23.4% solution to give us that amount of sodium chloride. This is going back to the last unit. These are easy questions. If that's my target, 12.7 grams of sodium chloride, and I'm using a 23.4 weight per volume solution. That means 23.4 grams per 100 mils. I stick the 23.4 in the denominator so that grams cancel, and I have found my volume of sodium chloride. I need 54.3 milliliters of this concentration solution to essentially provide me my 5 grams of sodium. But guess what? Now we got to do the same thing all over again, but now with the sodium acetate. This is just saying with my total of 15 times 2/3 gives me, I need the 10 remaining grams from sodium acetate. All right, take my 10 grams of sodium acetate, convert sodium grams into the number of moles of sodium, convert the moles of sodium to sodium acetate, because again, it's 1-to-1. Looking at the formula, there's just 1 sodium in sodium acetate. So then I can multiply by the molecular weight to convert moles of sodium acetate into grams of sodium acetate. So there's my target weight of sodium acetate, because this is the weight that contains 10 grams of sodium. So let's start with that and say, okay, if I'm getting it from a 16.4% solution, then again, I'm going to multiply by 100 and divide by 16.4 so that grams cancel. And I see that I need 217.7 milliliters. This is the volume that provides the weight of sodium acetate that provides the weight of sodium that I need. So I now have 2 volumes. I have a volume for my sodium chloride. I have a volume for my sodium acetate. Let's add those up. Basically, I'm going to take all of those and subtract them from the total. Remember, the whole point was to make 500 milliliters. Okay, so from 500 milliliters, if I subtract the volume of the sodium chloride, I need to provide 5 grams of sodium chloride, or 5 grams of sodium, and subtract the volume of the sodium acetate, that gives me essentially 10 grams of sodium. Then the difference is just the volume of water I would need to add. So to formulate this, I take 54.3 mils of sodium chloride plus 217.7 mils of sodium acetate and 228 mils of water, mix it all up, shake it all together, and I have exactly 3% concentration of sodium, divided out exactly the way I wanted between sodium chloride and sodium acetate. Okay? So the math wasn't hard, but that can be difficult if you're not taking the stepwise approach to what we're doing here. So that one's a little bit tricky, okay? Well, we can end this without an osmolarity question here, and I'll just, for the sake of time, we calculated the weights of the different sodium chlorides that we needed. So here I'm converting weights to millimoles, millimoles to milliosmoles by looking at the formula for each ingredient and calculating it, okay? And I do the same thing with the sodium acetate. Both of those are just 2 milliosmoles per millimole because of the formula. There's 1 and 1 for each of those molecules. So once I know these 2 together, I add them together, take that, and remember we're making 500 milliliters. Expressing 500 milliliters in liters is 0.5 liters. That's where we get a total osmolarity there of 2,612 milliosmoles per liter. All right, we still got a tradition here. What did I say each question was going to end with? A crappy question, so let's go back. And this is not endless practice problem. You definitely need to know how to do this. It's pretty straightforward. Just think about this. So I'm trying to have you learn how to calculate from weight to millimoles, and from millimoles to milliosmoles. A great example is, again, these electrolyte bow prep solutions here, because they have a lot of ingredients of it. I know I'm running out of time, so I'll just kind of show you here. But this breaks it up by 1 ingredient at a time. So polyethylene glycol 3350. Does anyone know what over-the-counter product that's in? Yes, there's an answer here. Miralax, very good. This is Miralax. This is what we do in Miralax. So one of the components is the same ingredient in Miralax. So if we're starting with 60 grams, I can convert grams to milligrams by multiplying by 1,000. All right, I gave the molecular weight, so I can convert the milligrams of polyethylene glycol to the number of molecules. And since it's a non-electrolyte, I multiply by 1 to get my milliosmoles. I hope you're getting the rhythm down with this. Anyway, so potassium chloride. Let's start with the weight of potassium chloride, convert it to milligrams, take the molecular weight and divide, so milligrams become millimoles. Look at the molecules. Potassium chloride is going to have 1 potassium and 1 chloride, so it's 2. So we multiply by 2, and that's where we got 20. Sodium bicarbonate, and this is real similar. I'm just going to show you here. 1 sodium, 1 bicarbonate, so it's 2. All right. Sodium chloride, 1 to 1, so it's 2. Okay, so that's all the same here. Finally, a little break in the monotony, and we could throw you off on an exam. There's an ingredient called sodium sulfate. So let me just back up and do the same thing again. 5.68 grams of sodium sulfate, converted to milligrams by multiplying by 1,000. Converted to millimoles by dividing by its molecular weight. Voila. Okay, but now we need to look at the formula. What does that dissociate into? How many sodiums are there? 2 sodiums and 1 sulfate. What is 2 plus 1? 3. So this is one where you'd have to multiply that by 3 to get the milliosmoles. All right, that was the only trick out of this whole question. That's a little bit different than the rest of the ingredients. So you had 1 ingredient, the PEG, which was a non-electrolyte, so it's 1 to 1. We've had 2 ingredients, or was it 3? I can't count, that were basically 2 particles for every molecule, and 1 now that has 3 particles from every molecule. In the end, you have to add each of those ingredients up, so the PEG, the potassium chloride, the sodium bicarbonate, the sodium chloride, and the sodium sulfate. Add all that together, add those up, and remember, this was a 4-liter preparation, so we divide by 4. That gives you the milliosmoles per liter.